G'day, welcome to the second video for topic 3 for week 10. This is a short one with a couple of questions relating to topic 3, which was radiation. As I said, there's only a couple of videos for this topic, so we'll jump over and we'll just work through these two questions quickly. The first question on radiation is about comparisons. We've got two identical objects in an identical room temperature environment. Object 1, though, is twice as hot in Kelvin as object 2. The questions, there's three things we have to compare. Which one of the two objects has the higher internal energy? Which one is absorbing the most radiation? And which one is emitting the most radiation? And then which one has the greatest magnitude net heat flow rate? So four different questions, four different things to compare. Have a go at it. As I always say, I'll repeat it again. Have a go at these questions. Don't just wait for me to explain them. Try and think about it yourself. Whether you get it right or wrong, it's a far better learning experience to attempt the problem and then get told the solution than it is to just watch the answers. And unfortunately, my mouse just jumped forward to the answers. But hopefully you all had a go at it by now. We will discuss these now. We've got first one, A, which has the higher internal energy. Well, hopefully you all remember that internal energy is just the total energy inside an object. Since these two objects are identical, we don't have to worry about their specific heat capacities or anything that would complicate it. If the object 1 is twice as hot as object 2, it must have twice as much internal energy. So object 1 is the answer for A. For B, which is absorbing the most radiation, remember that the absorption is based on the temperature of the environment the object is in. We've said that these are both in identical room temperature environments, so therefore they're both going to be absorbing the exact same amount of radiation. Because the objects are identical, so they've got the same surface area, the environment's the same temperature, so the absorption is going to be exactly the same. But for part C, it won't be the same. Which one is emitting the most radiation? Well, the hotter an object is, the more it emits. Since they're identical, we don't have to worry about their emissivity or anything else, just their temperature. The hotter object will emit more radiation. So for part C, the answer is object 1. And for part D, which has the greatest magnitude net heat flow rate? Well, the answer is that we don't know. We cannot tell from the information we have been given. Some of you may have thought that object 1 will be because it's hotter than object 2, and that would be based on the idea that object 1 and object 2 are both hotter than their environment, but we were never told that. They didn't say, or I didn't say because I wrote it, that the objects were warmer than the room temperature environment. So if we have an object that is in a 21 degree Celsius environment, and this object is at a, I should have done it all in Kelvin. So this is 294 Kelvin, right? It's 294 Kelvin, and we've got an object that's at, say, 400 Kelvin, and then we've got one that's at 800 Kelvin, so this is twice as hot. Then obviously this one is going to have, it'll be a net emitter, but only based on the difference of these fourth powers. This one will emit a lot more. They'll both be absorbing the same, so this one will have the greatest net heat flow rate. But what about instead, same thing, we've got 294 Kelvin environment. But what if we had one object that was, I have to do some math here. Let's say whatever number ends up being, I should have figured this out before, but let's say it's 100 Kelvin less, so let's say it's 200 Kelvin, and then this is 400 Kelvin. Then to make things simple, let's say that we've actually got a 300 Kelvin environment. So we got 200 Kelvin object, a 400 Kelvin object is it's twice as hot in Kelvin. The environment being at 300 Kelvin would mean that this one has a net flow rate in, and this one has a net flow rate out. Right? Actually, those numbers won't work exactly. But you can see that there would be a system where you'd actually have the same heat flow rate. It's just that one would be emitting and one would be absorbing. And then if they're both colder, if they were both colder than the environment, so if we had 294 Kelvin, and then we had 10 Kelvin, and we had 20 Kelvin, right? Now this one would have a greater net heat flow rate because it is further away from the environment temperature. So the point is you can actually get any scenario out. It won't necessarily be the hotter object is the greatest magnitude net heat flow rate. Hopefully I've managed to convince you of that with my ramblings there. So back to the questions. There's the answers. Next question, steel plate. A thin square steel plate with side length 10 centimeters has been heated to 800 degrees Celsius. Its emissivity is 0.60. What is the rate of radiation from the plate? And what is the net heat flow rate for the plate at room temperature? So two parts to this question. First one, just the rate of radiation. Second one, though, is talking about the net heat flow rate with a room temperature environment. So hopefully you've all had a go at this video this now. Otherwise, pause the video, do have a go at it. But I will jump over to my document camera and we'll work through this one. So first of all, we are told that the square steel plate has 10 centimeter sides. And that means that we have an area of 0.1 times 0.1 or 0.01 square meters into SI units, just because that's what we need for our equation. So we got 0.01 square meters. We got told that the emissivity is equal to 0.60, I believe it was. We hopefully recall, oh, no, we won't hopefully recall, we'll hopefully be able to go and look up the Stefan-Boltzmann constant of 5.67 times 10 to the minus 8, plus some units. Make sure you write the units down, right? I haven't, but make sure you do. And then we've got the temperature. The temperature we were told was 800 degrees Celsius. But that means that we have Kelvin, we have add 273, 1073 Kelvin. Right. Okay, so how much is this radiating? Well, the first thing to think about is the fact that the area, right, tells us how much is radiating, because every part of this is going to be radiating. But what about the other side? Right? The other side will also be radiating. So actually, we need to double our area. And there's no rule, there's no formula, there's nothing to tell you to do that, except for you to think about the scenario. So this is where thinking about the system, using your understanding of physics and what we're actually talking about is essential to be able to solve this problem. If you had just gone area is 10 centimeters by 10 centimeters, 0.01, right, you would be wrong because you'd only have half of the object being considered. You've got to think about both sides in this case. So that's our little adjustment that I wanted to point out. Now we can just use the formula. So delta Q by delta T is equal to A epsilon sigma T to the fourth minus, oh no, because this is not environment yet, this is just the object. So temperature of the object to the fourth power. So we've got all those numbers now, 0.02, 0.6, 5.67 times 10 to the minus 8, and 1073 to the fourth power. And if you do that calculation, which I'm sure you all have by now, you will get 902 watts. Right, so that is our rate of radiation. For the net heat flow rate, remember that it's the exact same formula, but it's now talking about the difference in temperatures. So this is the heat flow that is leaving the plate. But of course, there's constant heat flow into the plate from the environment as well. It's nowhere near as much because the environment is only going to be at about 20 degrees Celsius, not 800. So it'll obviously be losing a lot more than it's getting, but it will still be getting some. So let's figure that out. It's the exact same formula, but now with the difference in temperatures. So T of the object to the fourth power minus, actually, I will do environment minus T of the object fourth power. And hopefully what you'll get is that you get out a negative. So even this one should have really been negative because we're losing the heat. We're losing 902 watts. This one you'll get negative 897 watts. So the object is losing 897 joules per second. And so that's about the extent of the calculations we'd expect you to do for this this topic. Just being able to use that formula. As I said, though, you do have to be able to think about the scenario, think about the system, and make sure that you are using the correct values for the system, because sometimes there'll be little tricks like needing both sides of that steel plate. But that's the end of topic 3 and therefore the end of week 10. So I will catch you at week 11.